Right. If you look at the example in the book, and they say graph y equals log base 2 of x, they actually, what they do is they graph, if this is f of x, then they say, well, f minus 1 of x, f to the minus 1 of x must be 2 to the x. And that's something, why is that still up there? That's something that, you can come up with your table of values for that. And then just switch all the coordinates, x's and the y's. Plot those points, there you've got your graph. We should be able to do it by looking at it like this. Right? We understand that an exponential function, its exponential growth, it should look like something like that. And the inverse should be a flip across this line. So whereas the exponential graph had an asymptote on the x-axis, the logarithm has an asymptote on the y-axis. And where this one had a y-intercept of 1, this one has an x-intercept of 1. So it looks something like that. So it should just look like a mirror image, from this side to this side. And this is the line of symmetry right there. So notice, is this a function? Would it pass a vertical line test? Yeah. Is this a function? Yeah, that's why this property of, f of f minus 1 of x equals x. That's why it works for logarithms and exponentials, because they're both functions. Now, notice this other thing, right? The domain of the exponential is all real numbers. All reals. The range of the exponential is y greater than 0. Okay, now for the logarithm, go back to purple. Remember, when you find inverses, the domain of the original function is the range of the inverse, all reals. The range of the original function is the domain, x greater than 0. And that makes sense, right? X greater than 0. It never touches this line. This is an asymptote. It's always to the right. Yet it's still all real numbers.